Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will go over the CycleGAN paper to understand it properly, and in the next one, I will implement CycleGAN from scratch with Pytorch. One more thing, that over the next month, I will do many GAN or generative adversarial network implementation from scratch with Pytorch. So do subscribe, because you hitting the subscribe button is what keeps me motivated to do this. Let's start. So here I'm looking at the original paper. It was published on 24th August 2020, and the name of the paper was Unpaired Image-to-Image Translation Using Cycle-Consistent Adversarial Networks. So CycleGAN is an extension of the regular GAN architecture, and it involves the simultaneous training of two generator models and two discriminator models. And we all know that the regular GAN has only one generator and one discriminator. Now, what does CycleGAN do? And the paper says that in the very first page that given any two unordered image collection X and Y, our algorithm learns to automatically translate an image from one into the other and vice versa. And some examples are given here that with CycleGAN you can translate a Monet painting to normal photos. You can translate zebras to horses, summer scene to winter scene. These are some quick examples. Now quickly see why CycleGAN is called cycle and why does it have two generators and two discriminator. So this is the intuition of CycleGAN, and obviously we can see a cycle here, one generator. So I have X as a source image and Y as a target image, and I have one generator GX and the second generator FY. So the first generator, that is a GX, takes image from the first domain, that is X, as input and outputs images for the second domain, that is Y here. The other generator, that is FY, takes image from the second domain, that is it takes image from Y domain as input and generates images for the first domain, that is the result of FY will be X. So it's just a cycle that you input one image from this domain, then the first generator produces or generates an output which is Y, that is a second domain. Then this domain also feeds into the second generator, and the second generator produces output which becomes my first domain. And just because I have two generators, that means I also will need two discriminators, because each of the discriminator will discriminate the image generated by each of the generators. So CycleGAN is used to transfer characteristics of one image to another, or can map the distribution of image to another. In CycleGAN, we treat the problem as an image reconstruction problem. We first take an image, that is the input X here, and use the generator G to convert it into a reconstructed image in the Y domain. Then we reverse the process, that is from the reconstructed image to original image, using the second generator, that is F here. Then we calculate the mean squared error loss between the real and the reconstructed image. Now understand why does it called unpaired, the word here, and why it is an unsupervised algorithm. So in the second page of the paper, this is the most important kind of image for this paper. So on the left I have a paired image set, and on the right I have an unpaired data set of images. So traditionally, training an image-to-image translation model requires a dataset comprised of paired examples. That is a large dataset of many examples of input images X and the same image with the desired modification that can be used as an expected output image Y. And what do I mean by the word paired? That's very well written here, this point. That is, paired training data, which is the left dataset, consists of training examples Xi, Yi, and I of course ranges from I equal to 1 up to n, where the correspondence between Xi and Yi exist. That's what is called paired. But in CycleGAN, there is no correspondence. That is, I don't know which Xi is connected or mapped to which yi. Now, this requirement for a paired training dataset is a limitation because these datasets are challenging and expensive to prepare. For example, photos of different scenes under different weather conditions. And that's where CycleGAN came to solve this. The genius insight of this UC Berkeley group that brought CycleGAN to the world was that we do not in fact need perfect pairs. Instead, we simply complete the cycle. We translate from one domain to another and then back again. For example, we go from summer picture, which is in domain A of a park, to a winter one, which is in domain B, and then back again to summer. Now we have essentially created a cycle. Let's go back to my slide here. So after we essentially created this cycle, we complete this cycle, that is X goes through GX to produce Y, and then the output again goes through the next second generator FY to produce an image which is in the first domain. So essentially these reconstructed image after the cycle is completed should be same. But if they are not, we can measure their loss on a pixel level, thereby getting the first loss of our CycleGAN, which is cycle consistency loss. The most important feature of CycleGAN architecture is that if we have unpaired images from different domains without direct mapping between them, a CycleGAN model should still be able to translate images between these two domains. Hence, the model architecture here is comprised of two generator models. One generator, that is generator A, for generating images for the first domain, that is domain A, and the second generator, generator B, for generating images for the second domain, that is domain B. And the generator models perform image translation here, meaning that the image generation process is conditional on an input image, specifically an image from the other domain. So generator A takes an image from domain B as input, and generator B takes an image from domain A as input. And now talking about the discriminator, I have two of them in CycleGAN. The first discriminator, that is a discriminator A, takes real images from domain A and generated images from generator A and predicts whether they are real or fake. And the second discriminator, that is discriminator B, takes real images from domain B and generated images from generator B and predicts whether they are real or fake. And this is how it works in discriminator. I have four options of real and fake images. So the first one is domain A real images goes to discriminator A, and then it outputs real or fake, because that's the job of the discriminator. It just tells me that whether an image passed to it is a real one, that is they come from the real dataset, or their fake one, that is they were produced by the generator model. So that was option one. And then option B is domain B real images goes to generator A, which produces domain A fake images. Then that fake images from domain A goes to discriminator A, and then it produces real or fake decision. Then the third one is domain B real images directly go to discriminator B, and this produces real fake decision. And the fourth and final one is that domain A images first goes to generator B, which produces fake images for domain B. Then those fake images of domain B goes to discriminator B, and that produces real or fake decision. Now, one very important factor to note here is that the discriminator model in CycleGAN is implemented as a patch GAN model. Now, a regular GAN takes an image as an input and it outputs a single scalar value which signifies real or fake. But in patch GAN, looks how it works. So in patch GAN, we have a 256 by 256 by 3 image at the input. And the patch GAN works on these 256 by 256 image on a patch by patch basis. And in CycleGAN specifically, here in this architecture, the receptive field of the discriminator turns out to be 70 by 70 patches in the input image. So the patch GAN maps from the 256 by 256 image to an n by n array of output, and say the output name is X, where each xij signifies whether the patch ij in x in the image is real or fake. Here n by n can be different depending on the dimension of the input image. And what would be the patch ij in the input? Well, output xij is just a neuron in a convnet, and we can trace back its receptive field to see which input pixel it is sensitive to. So in practice, what this means is that PatchGAN architecture outputs a feature map of roughly 30 by 30 points. Each of these points on the feature map can see a patch of 70 by 70 pixel on the input space, and this is called the receptive field size. So in this slide at the very start here, this blue segment, the selected segment, that's the receptive field. So to be precise, the PatchGAN architecture is equivalent to chopping up the image into 70 by 70 patches, making a big batch out of these patches and running a discriminator on each patch with batch norm applied across the batch, then averaging the result. And the advantage of using a PatchGAN over a normal GAN discriminator is that it has fewer parameters than normal discriminator. Also, it can be applied to input images of different sizes, for example larger or smaller than 256 by 256 pixel. The output of the model depends on the size of the input image, but may be one value or a square activation map of values. Each value is a probability for the likelihood that a patch in the input image is real. These values can be averaged to give an overall likelihood or classification score if needed. And now, one of the most important concept in CycleGAN paper, which is cycle consistency. Let's look at this image. I have horse images and zebra images. Horse images belong to domain 1 and zebra belongs to domain 2. Now, domain 1, that is a horse image, is input to the generator 1 and that outputs zebra. Now, zebra is again input to generator 2 and that outputs back to horse. And then this output from the generator 1 should match the original input because both belongs to the same domain 1. But if they don't, that is after the horse input image goes through generator 1, then again generator 2 and produce the horse again, if these two are not similar, then that becomes my loss, and that loss is called cycle consistency loss. So the idea here is that an image output by the first generator could be used as input to the second generator, and the output of the second generator should match the original image. And if I go to the original paper, they also give a nice diagram for this cycle consistency loss. And here is that diagram. What they are talking about is our model contains two mapping function. The one is G, which maps from X to Y, and F, which maps from Y to X, and associated adversarial discriminators dy and dx, which dy encourages G to translate X into outputs indistinguishable from domain Y, and vice versa for dx and f. To further regularize the mapping, we introduce two cycle consistency losses that capture the intuition that if we translate from one domain to the other and back again, we should arrive at where we started. And so this part of this section of this diagram is what is representing cycle consistency loss. So first look, X is X is the input here, and that goes to the generator G and produces Y. Then Y is again input to the generator F, and that produces X back. Now this original X and the reconstructed X after these two cycles should be same theoretically, but actually they are not same, and that difference is what cycle consistency loss. And the opposite way of movement is also true, that is in the third section, that is the C section of this entire diagram. Here I am starting with Y, that is input to my generator F, and then I get X, and then that X is again input to the second to the generator G here, and G will produce Y. So the starting position from this y domain goes through two generator to produce the original y again, and theoretically they should be the same because they belong to the same domain, but they will not be exactly same, and to the extent they are different, that is cycle consistency loss. So the cycle consistency is a concept from machine translation, where a phrase translated from English to French, for example, should translate from French back to English and be identical to the original phrase. The reverse process should also be true, and so that's the cycle consistency concept. And obviously, to be able to use cycle consistency loss, we need to have two generators, one translating from A to B and then another one translating from B to A. And that also means there will be two losses. One is forward cycle consistency loss and the other one is backward cycle consistency loss. So here in this image, when x is converted to y and then y back to x, this loss is a forward cycle consistency loss. And then in this part of the diagram, when we start from y, go to x after first generator, and then again it cycles back to y, then this loss, that is the difference between this original y and the reconstructed y, this is called backward cycle consistency loss. And that's exactly what the paper talks about. I have put that part in this red border. That is forward cycle consistency loss. Here x goes to gx, then the output of this entire gx goes to the f function again. That is the next part. This one here is f of gx. That should produce a reconstructed x. So the loss here is a forward cycle consistency loss, and then the backward cycle consistency loss is where y goes to fy, and then again the entire thing goes to the second generator, that is g of fy, and then that should produce the reconstructed y, like in this part of the diagram. And this loss here, that is the difference between the original y and the reconstructed y, that's my backward cycle consistency loss. And obviously all of these will be much more clear when in the next video I will implement these from scratch with Pytorch. Just another example of forward cycle consistency loss while translating summer images to winter images with CycleGAN. So first step, input photos of summer to GAN1, then output of these GAN1 will be winter images. Then take those winter images and pass them as input to GAN2. Then GAN2 will produce summer images again. That is, after the original summer images, after these two GAN cycles, comes out to be summer images again. Now compare the summer images here, that is a reconstructed summer images, with the original summer images, and that will be your cycle consistency loss, and which is forward cycle consistency loss. Now exactly the same process but in the opposite direction will be your backward cycle consistency loss. So in this case, input photos of winter to GAN2, that will output summer images. Then input those summer images photos to GAN1, that is the output of, take the output of GAN2 and pass them as input to GAN1. Then output of GAN1 again will be winter photos. Now compare these reconstructed winter photos after these two GAN cycles with the original winter photos, and that will be your backward cycle consistency loss. And so now that we understand very well the cycle consistency loss, that is both backward and forward, now let's go to the section of the paper which talks about the most important part of overall loss calculation. So here is that section in the paper. Obviously, after our discussion, the total loss will be constructed by adversarial loss and cycle consistency loss. So the first one is this adversarial loss. This is the regular GAN loss. So this equation should be familiar with you who are already conversant with GAN. So I put some comment here. Let's see what I put. So this is regular GAN loss or adversarial loss for the mapping function G which produces a map between x and y, that is it takes x as input and produces y, and the corresponding discriminator is dy, and here G tries to generate images gx that look similar to images from domain y, while dy aims to distinguish between translated sample gx and the real samples y, obviously. And similar adversarial loss for mapping function f, that is which maps from y to x, and the corresponding dx are also introduced here. So yeah, so this is a regular GAN loss, and I have two of them because I have two generators. And then I have cycle consistency loss, all this discussion that we had a minute before. So now this section, actually they mention it very clearly that why cycle consistency loss is needed at all. Let's quickly read through this section because this is very important actually. So adversarial training can in theory learn mappings G and F that produce output identically distributed as target domains Y and X respectively. However, with large enough capacity, a network can map the same set of input images to any random permutation of images in the target domain, where any of the learned mappings can induce an output distribution that matches the target distribution. Thus, adversarial losses alone cannot guarantee that the learned function can map an individual input xi to a desired output yi. To further reduce the space of possible mapping function, we argue that the learned mapping function should be cycle consistent. Okay, so basically what they're saying is without the cycle consistency loss, I can have one input image mapped to multiple output image in the target domain, and that's a problem. So that's why cycle, this very important concept, this is actually the brilliant concept that was brought to the world of generative adversarial network, that is the cycle consistency loss was brought in this paper. And to calculate the cycle consistency loss, here is the equation for that. And what they say in the section B is for each image X from domain X, the image translation cycle should be able to bring X back to the original image. That is, X goes to GX, then again I take F of GX, that is X goes to 2 consecutive GAN cycles, and that should bring the original X back. We call these forward cycle consistency. Similarly, as illustrated in figure 3, for each image Y from domain Y, G and F should also satisfy backward cycle consistency. That is, in this case, Y goes to Fy, that is one generator, then it goes to the next generator, G of Fy, that is after Y goes through 2 generator cycle, the original Y should be back. And we incentivize this behavior using a cycle consistency loss, and this is the equation. The equation is very simple. For they are basically calculating the L1 loss, that is F of GX should be ideally the original X, and if they are not, that is the difference represented by F of GX minus X, and that's my forward cycle consistency loss. Similarly, for the backward cycle consistency loss, this is the second part, that is G of Fy should be equal to Y, but they are not, and that difference is my backward cycle consistency loss. So now I have adversarial loss calculated here and the cycle consistency loss calculated here. So the total loss will be, that is the full objective is represented in this equation. So here I have the adversarial loss here for the one generator, then the adversarial loss here for the next generator, and finally my cycle consistency loss. And this variable lambda just controls the relative importance of the two objectives. So lambda is just a weightage factor here, that is to what extent I should weight the different part of this overall loss objective. And then the next part of the paper is about implementation of the entire architecture. Of course, these implementation details will make much more sense when in the next video I'm going to actually implement it with Pytorch. So basically what they are doing is that this network contains 3 convolutions, several residual blocks, two fractionally strided convolution with stride half, and one convolution that maps features to RGB. And also they're talking about we use 6 blocks for 6 residual blocks actually for 128 by 128 images, and 9 blocks for 256 by 256 images. All right, and for the discriminator network we use 70 by 70 patch GANs, which aim to classify whether 70 by 70 overlapping image patches are real or fake. On the same line, on the training guidelines, we apply 2 techniques from recent works to stabilize our model training procedure. First, for LGAN, that is equation 1, which is my this one, that is adversarial loss. What they're talking about is, for equation 1, we replace the negative log likelihood objective by a least square loss. This loss is more stable during training and generates higher quality results. All right. So that means they are using MSE, mean squared error, which will be the expression, mathematical expression will be just this, that is for each of the GAN. So the first GAN, d of gx minus 1 whole square, and the train the d to minimize dy, that is discriminator y minus 1 whole square, plus this one dgx square. Okay, again, this will be much more clear during my implementation in the next video. Anything else here? Let's quickly see. Yeah, they have a section where okay, this is also important, analysis of the loss function. What they saw by using different aspects, different way of calculating the loss. So removing the GAN loss substantially degrades result, as does removing the cycle consistency loss. We therefore conclude that both terms are critical to our results, that is both the adversarial loss, which is a regular GAN loss, and also the cycle consistency loss. Both are equally important for this architecture. We also evaluate our method with the cycle loss in only one direction, that is GAN plus forward cycle loss or GAN plus backward cycle loss, and find that often it often incurs training instability and causes model collapse. Okay, this is also not acceptable. That is, I cannot implement just one directional cycle consistency loss. So whichever directional cycle consistency, so basically the paper says that if I remove only one direction cycle consistency, that is either remove the backward or the forward cycle consistency loss, then there will be instability in that direction, and also you will face a mode collapse for the direction of the mapping that was removed. And finally, in the appendix section of the paper, they also give some more details on the network architecture. So they're saying we use 6 residual blocks for 128 by 128 training images and 9 residual blocks for 256 by 256 higher resolution training images. And then they give the very important part, which will, these details obviously will become much more clear when in the next video I will actually implement these structures. So basically they give every details of what kind of convolutions, stride and padding and filter size you have to use for your generator and the discriminator architecture implementation. So let CS S1K denote a 7 by 7 convolution instance norm ReLU layer with K filters and stride 1. In that case, a network with 6 residual block consists of C7S1. That is, I will have the 6 residual block. Each one will consist of a 7 by 7 convolution instance norm ReLU layer with K filters, and K in this case is 64 and stride is 1. So that's how you have to read these terminologies here. And about the D256 or D128, they say that DK, so this D128 is my DK here, and denotes a 3 by 3 convolution instance norm and ReLU layer with K filters and stride 2. So this will be my 3 by 3 convolution instance norm and ReLU filter with 128 filters and stride of 2, and this will be 256 filters with stride of 2. And about the R, the reflection padding was used to reduce artifacts. RK denotes a residual block that contains 3 by 3 convolution layer with the same number of filters on both layers. All right, and of course the most important point to note in this architecture is that here we do not use a batch norm, instead we use instance norm. And about the discriminator architecture, for discriminator networks we use 70 by 70 patch GAN. Let CK denote 4 by 4 convolution instance norm leaky ReLU layer with K filters and stride. And also we do not use instance norm for the first C64 layer. We use leaky ReLUs with slope of 0.2, and then the discriminator architecture is just this, that is a 70 by 70 patch GAN with a 64 filters of 4 by 4 convolution instance norm and leaky ReLU. Then I have C128, that is 128 filters, then 256 filters, and finally 512 filters. And they're also saying clearly that for the C64 layer we do not use instance norm. And another very important concept of CycleGAN is the concept of identity loss. So let's look at this image. So here the original input is here, and this second column represent without identity loss the result, and the third column represent with identity loss the final result from CycleGAN. So the idea here is that the identity loss, in identity loss we want to enforce that CycleGAN preserves the overall color structure or temperature of the picture, and this is done by feeding the images already in domain A to the generator from B to A, because the idea is the CycleGAN should understand that they are already in the correct domain. In other words, we penalize unnecessary changes to the image. So if we feed a zebra to a generator that is supposed to generate a zebra, then we should get back the original zebra, because there is nothing to do. So basically with identity loss we introduce a regularization term that helps us keep the original image or the overall color structure and temperature of the original image consistent. So imagine this as a way of ensuring that even after applying many filters onto your image, you still can recover the original image. That pretty much wraps up this video where we understood the architectural details of CycleGAN, and in my next video that I will publish in next couple of days, where I will implement CycleGAN from scratch with Pytorch. And finally, over the next couple of months, I will do many popular GAN or generative adversarial network implementation from scratch with Pytorch. So stay tuned and do subscribe. Thank you very much for watching. See you in the next one.